Thanks so much for the invitation. Today we're going to talk about why we should investigate M2P reactions, methane to other products, in this case, methanol. So I'm going to show you some topics, the introduction, why this is important, and our main goals that concern my postdoctoral project, the methodology that we are using, some of our results, and our present work in some perspectives. So why the importance of use methane for new energies? I will show you some predictions that now we are living on a quaternary phase of a new energy era. So we are, I don't know where the pointer is, but we are dealing with four type of energy until with a little bit of coal and oil and natural gas. If you see the projection for more 50 years ahead, we can go, this is going to change. When for now, today, how which strategy that we have to use? We can, one of the best answers. It should use the intelligent use of non-renewable resources like natural gas. So this is important because natural gas is primarily composed by methane, which is one of the most unattractive precursors of C1 chemistry. So however, use methane to obtain other parts is a challenge because everyone we know that it's a stable molecule. It has symmetry, tetrahedral symmetry, and in this case, it's difficult to remove the hydrogen. It has a pKa, and for instance, to remove this hydrogen is necessary at least 435 kilojoule per mole. So one of the strategies here is to use different type of materials to decrease the energy necessary to break the molecule, since it is needed to activate methane. Is the first step to activate methane is to break and remove this hydrogen. So different types of materials have been used so far, like nanoparticles, transition metal nanoparticles, oxides, nanoparticles supported on oxides on surface, amorphs and graphene and others. So in a theoretical point of view and also experimentally, we have to understand the whole process from the adsorption process of this molecule, the activation process, and the distortion of the products. So I'm show you some of the complicate challenging for us, because this is just a few reactions, common reactions methane to methanol using O2 as a font of oxygen. So we can separate in different groups, like the first step, the distortion of this molecule on the substrate, and then the hydrogenation process that is common occurs in especially nickel catalysis. Then we can these hydrogenation species can yield new products. Like the first step, you can obtain methanol, but it's really hard. Then all the products can also suffer from dehydrogenations. So you have to look for all the process of this mechanism. So we have the direct reactions. The indirect reaction, we have a proton hydrogen abstracting before to yield the product. Then the product, the hydrogenation, and also the side products. So to model this type of reaction, you also want to choose, and in agreement with experimental results, the kinect involved. So we have for this type of heterogeneous catalysis, we can obtain for experimental and theoretical two types of mechanisms. That source, they both starts equal and finish in the same way, but the intermediary adsorptions is a little bit different. But for example, the first one, we have the distortion of the molecule, and then the subsequent steps, the transition species are also absorbed. But we have cases that the transition species are in gas phase too. So in my work, we are dealing just in the beginning of a dehydrogenation process. So we model that all species are absorbed in the substrate. So our main goal here it was understand the methane hydrogenation on a 3D transition metal cluster, 13 atoms. So we choose as to iron, copper, nickel, and cobalt to start. And we applied different methodologies to achieve not only thermodynamic properties but also kinetic properties. So in the first step, we choose the substrate from our previous works. You optimize on your level of theory, and after the substrates choose the lowest energy configuration for this representative set, we had search the pre-optimized species, methane, CH3, CH2, and 2 carbon. Then we from any million configurations, we reduce the set for a smaller one with our in-house algorithms. And then we perform the GFT optimizations with FAJM's analysis. Then for each set, we have a representative structure. A second approach was to take into account the hydrogen adsorption, like we are dealing with the hydrogen end process. Most of this hydrogen can be absorbed in the substructure. So he performed the hydrogenation process, and we take the structure, the lowest energy adsorption configuration for the previous step, and do again a new adsorption for the new molecules, the new systems. So for example, if you want to absorb CH2, we absorb 2 hydrogen atoms. For C, 4 hydrogen atoms until complete all this CH4 molecule. Uh, However, if you want to have some kinetic properties from the system, we have to separate them for elementary steps. So in order to achieve that, we did another methodology when we kept fix the molecule and just did one adsorption of one hydrogen. So to mimetize the elementary step from the hydrogen process. So we start for the lowest energy configuration from the first step, and then we fix the molecule in the same place, and then we was the one hydrogen one abstract for each step. Then we have a new set of different one new representative set with just one hydrogen adsorbed on the system. Well, everything was performed with FAJM's program with GFT and as well with one develops corrections. Now, I will show you this because the first time I think I'll get someone is using in our group is a methodology called a method called the unit bond index quadratic exponential potential method, UBI-KIP method, that was proposed in the 80s by Storovich, that you can can get energy barriers from adsorption energies. So what this is a hybrid semi-empirical method. I will explain why. As you can see in the equation, the energy of a molecule, an energy barrier for a molecule that is a transition state of CH3, CH2, CH, can be obtained by the absorption dissociation energy from the same molecule at the gas phase, and this can be inputted in this equation by GFT methods, by coupled cluster, and also by experimental. So it's your choice. Choose what association energy you can put in the equation. And then all parameters that you need is the absorption energy for the subsequent species. So if you want to study the energy barrier for CH4 to yield CH3, you need the absorption energy for CH4, CH3, and the absorption energy of the other molecule takes part, the hydrogen. The what I call revised method, because in the first, as proposed by Storovich, this is applied on the surface, and then the hydrogen absorption is take like is in an average value. In this case, we have done another calculations to retrieve the absorption of the hydrogen in the cluster. So we can this is change for each system that we are dealing for. And I want to highlight that this activation energy barriers is sensitive to the FT approach. So you can have the tenders, but you can have the value, the right value. Uh, since because you have to use van der Waals quotations and also ZPA corrections in that social energy. They are direct depending from how you obtain that social energy. So despite these fluctuations of this method, you can compare with other type of other methodologies available like NEB. There is a new paper of Abud Peterson that from SunCat group that compare directly this methodology, of course, revised with a new formulation, with NEB calculation and string matrix calculation. It has direct correlation with that. So we can make sure to use that in our work. So these are perfect results. So we have found that the distortion increase with the data generation process as we expected, and then we have a comportament that is useful to use the by keep method, since we have found that the carbon atom tends to maintain the 5 or 4 coordination number. So we will show you only our also results show that nickel serves stronger than iron, and cobalt was almost the same magnitude, and there was distortion interactions is with copper. As we expected, this is really agreeing to meet all the experimental reports. And also, if you look to the graphic, there is a deviation in CH to C4 copper that is in blue, where it shows that source of CH is preferred than carbon. This is also in agreement that in copper, the tendency to form carbon deposition in copper is not observed. So we also did the same analysis to see the effect of hydrogen co-distortion, how it can change the magnitude of the distortion energy. And also we saw that the increase the distortion increased its magnitude when we consider the co-distortion effects. This is some preliminary results here. I showed the relative energy, although as a different way to show the reaction path for this system. When we compare the tendency of the formation of this the hydrogenation species from in comparison with the gas phase molecule, methane gas phase molecule. And as you can show you, nickel has from up to down, you have isothermicity, and down to up in the same line, you have endothermicity of the system. So you can see that we have the nickel has a tendency to form an CH3 better than it also go to do the methanol, then better than the iron and copper that is way in the scale energy. So, but also we can, if you look to nickel and cobalt, we see that they have similar values of delta 8. So we have thermodynamic nickel only is preferred to form this type of system, but when you compare cobalt, they are compete with each other thermodynamically. So when the point of view of iron and copper, this is a really different. Copper, we have the most stable system is a distortion of methane, and this not and the preference for CH3 is not we can is almost none. So this is also in line with the when we use we see also the preference for copper to form carbon in this type of graph. We also show that it requires a lot of energy, which is also in line with the experimental results and found the distortion results. So why now we have been why we are seeing these tendencies for this type of systems? We did a lot of other analysis, like Hirschfeld analysis, electron density difference analysis, and now I will show you only one of the PEDOS. That we have the two extreme systems, nickel and copper in that way, and we see that with the hydrogenation process we have a better coupling between the d orbital from the metal with the p orbitals from the molecule that is absorbed. So this is increasing with the hydrogenation process, and this shifts also broadening the the lumen stays towards more positive energy levels, which is also you can also understand this that the band model. It's also which is in line with the band model. So what difference when we see what the Cooper that the social is not so uh, this magnitude also is the smallest one. First, we have the occupation. The occupation of these states, the push forward to more energy, negative energy levels, the D band, in the discouple between the d orbitals with the p with the CH does not occurs as occurs for nickel, cobalt, and iron. And hence, when we compare the hydrogenation, the absorption of the hydrogenation, we also see that this is increased with the which also which explain the larger magnitude with the hydrogen absorption for the absorption energy and interaction energy for this process. And as a result, also I can show you now that we can predict the energy barrier for each step from the schematic methodology, where this will show you that this is for Cooper and without any ZPI, it's almost primary results with VDW corrections. This is changed a lot in almost an and a half when you use both VDW and ZPI corrections, but we only change the magnitude, but the tendency is maintaining the same. And we can see that from the this from CH to CH C plus the last step of the generation process, there is a high energy barrier to formation to carbon. This is also in agreement with the experimenters that on Cooper-based materials like surface and so on to form carbon depositions. And this is when you compare it to nickel. This is a nickel. The energy barrier for nickel is pretty small. So these are some of our results. And with all knowledge that we are covering here is we are looking for the study, the Beneath study Aubert and Protect Copper and Zinc alloys that is being performed by Gianluca. And now he's starting study only the united clusters. From in this project, the main goal is to understand the effect of size on these clusters, and then we are going to investigate the binary class and elucidate the effects of the CP star linked into the properties. So and also in the future, we want to also investigate the this system are uh, can show any catalytic properties for methane activation, which are in line with your work. The second project that is going on about is the Benish screening of better and protect alloys with a fixed composition. This is being performed by Philippe, who is there. He's here. And now he's studying only the united clusters. And this we want to understand uh, the effect of the nature of the transition method used in the different properties. Then we want to elucidate the effect of CP linked on these alloys, and also in the future investigate the catalytic properties for CH4 activation. So what we have been learning and from my work, we are going to use for these two works. So thank you so much.